I mean, I've got this new microphone. It's got a kind of cover. I thought that was going to get rid of all the plosives, all the I don't know. Yo, what's up, Internet? Since Media here, and we are back in Protoplug, and I'm going to make another change to our Protoplug based synthesizer. So last time we were doing wave folding. Now what I've done is I've added a phase modulation, which is kind of like a frequency modulation. So the basic idea behind phase modulation, I think, is explained actually very well by this diagram here on the right on this Wikipedia page about it, phase modulation. So if you look at this brownish wave here, it's a sine wave, and that's an ordinary wave, which is the carrier wave. It's the wave that's going to be modulated. And you can imagine that this blue line here is reading the value of it and sending it to the final output. But as you can see, this blue line is not staying constant at time t. Instead, it's shifting a little bit in front of this time t or a little bit after it. So it's actually shifting within the wave that it's, let's say, reading from. And what controls how much it shifts by is the second sine wave here, which is called the modulating wave. And the modulator is slightly shifting the position within the phase, within the carrier wave that you're currently reading. And where you're reading comes down to here with this grey wave, and you can see it's a more complex wave than either of the two sine waves. It's not a simple interference pattern between the sine waves either. It's created by using the modulator to shift the read position within the carrier. So that's how you achieve phase modulation. The phase is the position here within that we're reading from. Now, if you remember my tutorial on doing FM synthesis in pure data, what we did there is we did real frequency modulation. We actually wobbled the frequency of the carrier wave according to the modulating wave. In this case, you can get a very similar effect, I think actually slightly more computationally efficiently, by simply switching, by modulating the read position within the phase of the wave. But you'll hear in a second that the effect is pretty similar. But it's worth, if you want to understand more about the background, it's worth reading this Wikipedia page. I think it's actually pretty good. So I'm in FL Studio. I've got a simple pattern being played here. Here's that wave. It's a sine wave pattern, current sine wave. And here is our synthesizer. So, as before, we've got the same things as before. We've got our wave folder. As we turn wave folding up, those extra harmonics come in. We get almost two folding twice, and then it turns into a square wave up here. Back to a sine wave. So that was where we left our synthesizer in the last tutorial, with this now wave folding oscillator. So what we have now is phase modulation, and the control I've given you for that is the phase modulation ratio. Now that's the ratio between the frequency of the carrier wave and the modulating wave. What you find is that obviously these transform the quality of the sound a lot. If you have them completely independently, you'll get a lot of sounds that sound completely different depending on the pitch of your initial carrier wave, which can be what you want. But if you're trying to make an instrument that's still able to sound a little bit more melodic, you can kind of pick up on what the pitches are, then a good way of doing that is to represent the amount of phase modulation you're doing in terms of a ratio between the original carrier wave and the modulating wave. So if the modulating wave could be twice the frequency of the carrier wave, or half, or something like that. So that's what we're doing here with this ratio. So now let's have a listen to just phase modulation. I'm going to start off with, when it's 0, we're not actually modulating at all. Then as we bring it in, it's a small proportion of the frequency of the carrier. And in fact, when it's really low frequency relative to the carrier, you can hear it's actually wobbling it a bit. And then as we bring it up, when it's about 1, again, it's very little effect. About 2 starts to give it this kind of chiming bell-like tone. Same with 3. Now we're up to about 5, so it's sort of starting to dominate. So like FM synthesis, again, phase modulation, sequence synthesis gives you these kind of chiming, metallic sounding, bell sounding tones, but in a constrained way. Let's take that and pitch it up now. Without the phase modulation, there's an example where you can really hear it at a very, this is just 0.05 of the frequency, so you can really hear how it's just wobbling it a bit. So that's the basic idea of phase modulation, and you can see it immediately giving us a whole new vocabulary of timbral effects to add to our wave. And we can of course combine it with the wave folding as well. At this point, the wave is completely a square wave. So we can really start making those bell-like tones, those metallic. We get a certain amount of high frequency. If we were to use the low-pass filter now to cut that off, we can clean that up a bit. the time we've taken that down, we've taken all those extra harmonics away anyway. Right, so let's have a look now how this is actually implemented. And as in an earlier example, what I'm going to do is I'm going to show you the diff of the previous version of the code and what I've now added to add this new phase modulation functionality. So we can ignore this thing at the top here, which is just the comment, and you'll see that again the envelope's the same, etc. So the first big difference is here when we come to this make oscillator function here. And remember, the oscillator's got things like the frequency, the amplitude, it's got this delta. Now, this delta is very important. The delta is the step increment. Every time we step through the building up our wave, every time we step through the sine wave, we increment the angle by this variable delta. That's the step increment of the phase that we're doing. Now, that was in the previous one, but now you're going to see how we change that. So we've got two new variables here. One is called the PM ratio, the phase modulation ratio, and one is called mod phase. That's the phase itself. Now, all the real magic, all the real kind of interesting work goes on in this line here. So let's look at the original version of this. If you remember, we define a variable s and we call the math sine function of the phase. The phase is the actual point we're reading through the thing. If you remember, it's like this point here, t, where we're actually currently reading off the sine wave. And if you remember, if we come down to the end here, every step we incremented the phase by the delta. Okay, so as we're stepping through that sine wave, we've got this value phase and we've got this value delta. Phase is the position within the wave, delta is what we're incrementing by at every step. Okay, so now we've got these two new variables here, and now what we're going to do is we are not simply going to take the sine of the phase itself, but we're going to take the sine of the phase plus the sine of the mod phase. So the mod phase is the position on this wave here, and we're taking the sine of that, and then we're adding to this phase, this time t, we're adding to this phase that difference that comes from the sine of the modulating wave. So although that's a complex idea, in terms of the actual representation in code, it's as simple as in this expression here, not just taking the sine of the phase itself, but the sine of the phase plus the sine of the mod phase, the modulating phase. And that's really doing all the work for us. That's doing all of the turning that simple sine wave now into something which is being phase modulated. Okay, so the phase modulation part itself, well, previously the phase in this oscillator was simply being incremented by delta. That's still happening here, but now we have a new line which is this mod phase, which is this extra bit. So the bit that's reading through this wave here, the modulating wave, that is now also being incremented by the delta. Remember, the delta is what the original is being, multiplied by the PM ratio. So the PM ratio is the ratio. So what that means, let's say the PM ratio is 1, so there's no difference. Well, you're simply multiplying the existing delta by 1, so it makes no difference. If the PM delta ratio was 2, it means now that we're incrementing the mod phase by twice the frequency. In other words, the frequency that the modulating wave is going past is double the frequency that the carrier is going past. Similarly, if the PM ratio was 0.5, then we would be incrementing or going through this wave only half the frequency or the speed as we're going through that wave there. So it's actually pretty simple in terms of the code to add this phase modulation to our existing oscillator. Now, of course, this code will be available for you to study. It will be in the same Git repository that I created. I'm going to stop using gists now. I'm going to just keep the state of this synthesizer in that Git repository. Right, then there's just a couple of extra functions here. There's a reset mod phase to 0. I'm not using that currently. I had an idea that maybe I would reset it to 0 at the beginning of the cycle. And that kind of gave an interesting effect, but perhaps not such a usable effect. And then there's just the set PM ratio function, so for updating the ratio within the oscillator. When it comes to the main sort of global variables, although they're called local here, these are the global variables. We also have a global PM ratio. If you remember, this PM ratio here is the one inside the oscillator, so every oscillator has got one. This is our global PM ratio here, and at this point within the actual process block, this is where we actually start using those oscillator objects to fill in the buffer. All we're doing now, every step we are setting the PM ratio of oscillator 1 and oscillator 2 to the PM ratio of this global PM ratio here. So when we, in the user interface, we update the global PM ratio, we're going to be changing the PM ratio in both of the oscillators in the same way. We could make it a little bit more complex and have independent PM ratios for the two. That might make for a more interesting sound. It might become a bit too chaotic to think about. It's, you can try that yourselves if you like. So that's it, basically. We've got a global PM ratio. Here's where we make that global PM ratio gets to update the oscillator. Inside the oscillator, the PM ratio just determines by how much we update the mod phase, and the mod phase determines what little bit of extra gets added to the phase itself, where we're reading off the carrier wave to produce the final wave. So I hope A, that makes sense, and B, you can see how it didn't require very much extra code to add quite a big chunk of functionality here. So that's it. That's all that really is there. The final thing is just we've added a new, in our user interface, we've added one more slider, the PM ratio. I've set it between 0 and 5, and when you change it, we just update this global PM ratio. So that's it. That's all there is that's new in this, and the end result gives us this new capability. An FM synthesis or phase modulation synthesis type thing. Interestingly enough, although Yamaha DX7 is obviously very famous as like the first commercial or first sort of popular FM synth, as I understand it, it isn't actually doing real FM at all. It is actually doing phase modulation synthesis. So it is the sound of the DX7 here. But the Casio came with, I think, their CZ range, was it? The CZ range, yeah. Phase distortion was their version of it. But they are all similar principles, right? They're all about changing the carrier wave according to some modulating wave. So let's just listen to it a bit more. And what's fun now is hear how we can combine these. And remember, we still have our low frequency oscillator, which is doing a kind of amplitude modulation. We can bring that up a bit. That is also got a wave folding. If we take it over there, that becomes a square wave. Play with our filter a bit. Some of these combinations have a bit of a tendency to make it disappear altogether. I'm not sure if that's because of some aliasing quirk. Put some supermassive on it. Alright, I'm going to do it. Yeah, right. So that's it. Just basically go get it. Where are we? It's going to be here. I'll put the link in the description. Current, the next state. It's not there yet, but it will be soon. And yeah, get it from there. Have a play with it. Make some changes. See what you can do with it. If you want to try adding separate any of these parameters, one for each of the oscillators, or perhaps let people play with the phase modulation of the LFO, then go for it. You know, there's lots to be done. The whole point of having the code is you can now get in and rewire this any way you like. Add more oscillators, add 3 LFOs, whatever. It's all there. It's just code. So thanks for watching, and I will see you probably with a very different subject, a very different topic in the near future. Thanks for watching.